A sterile, rocky expanse does not remain barren forever. It transforms into a dense canopy through a highly predictable sequence of migrating plant communities. We define this process as ecological succession, a directional change in community structure from a barren environment to a stable one. This continuum has two distinct entry points, depending entirely on the severity of the initial barren state. Primary succession begins on completely sterile areas with zero initial soil. Secondary succession starts in disturbed areas where an intact soil bed exists. This initial soil dictates system velocity. Primary succession takes millennia, while secondary succession rapidly accumulates biomass in decades. The origin state dictates recovery speed, but the mechanics do not change. Both pathways are governed by the exact same architectural blueprint of community assembly. Here is the 5-step engine that mechanically drives a landscape from absolute sterility to a stabilized climax state. Step 1 is nudation. The process can only begin when a localized area is completely stripped of life, creating a blank canvas. 3 forces cause this clearing: topographic events, extreme climatic shifts, or biotic interventions. Once cleared, step 2, invasion, begins. But the true bottleneck is ecesis, the successful germination and establishment of a plant, which is statistically rare in hostile conditions. To survive the ecesis phase, pioneer organisms must withstand intense heat and low moisture to anchor their root systems into the substrate. The entire ecological future of a massive landscape hinges on the microscopic success of these initial pioneer seeds. Once ecesis is achieved, those surviving populations reproduce and group together, moving the system to step 3, aggregation. The immediate consequence of aggregation is fierce competition. As populations cluster, individual plants engage in battles for a finite supply of space, light, and soil nutrients. This interaction triggers step 4, reaction. This is where living organisms begin physically altering their abiotic environment. These organisms shift soil pH by dropping acidic leaf litter. They retain ground moisture through root networks and increase canopy shade, lowering the temperature below. Plant roots exude chemicals that restructure the soil texture and change the color gradient as they modify the habitat. We classify this as autogenic succession. The process relies on the biological community itself driving the chemical and physical changes, rather than external weather or geological forces. This leads to the ultimate irony of the reaction phase. By modifying the habitat to survive, pioneer organisms engineer their own obsolescence. They alter the environment until it perfectly suits the biological replacements that will outcompete them. In 1977, ecologists Connell and Slatyer defined the 3 distinct mathematical pathways early colonists use to dictate the arrival of later species. The first pathway is the facilitation model. Early species actively prepare the ground, making it highly favorable for the next successional stage. For example, alder trees fix nitrogen into barren floodplains, changing soil chemistry to enable the later dominance of spruce trees. The second pathway is the tolerance model. This is a neutral pathway. Later species are neither helped nor hindered by the pioneers that preceded them. In the tolerance model, environmental preparation is irrelevant. Species replacement is driven purely by superior life history traits and a higher tolerance for intense resource competition. The third pathway is the inhibition model. This is an antagonistic pathway where pioneers suppress and exclude any new arrivals through strong competitive interactions. Under inhibition, the succession timeline is temporarily frozen. The community will only advance when an external disturbance or natural death removes the inhibiting early species from the board. Ecological turnover operates as a complex matrix of active facilitation, total indifference, and localized biological warfare. The final community structure depends entirely on which of these forces wins out over time. Eventually, the rapid species turnover slows. The system enters step 5, stabilization, reaching the theoretical endpoint of all these models, the climax community. This diagram illustrates the principle of environmental convergence. Whether a succession begins in a flooded pond or on sun-baked rock, biological reaction continuously pushes the environment toward a balanced intermediate moisture state. This table contrasts pioneer stages with the final climax. Pioneers use open nutrient cycling, while climax forests operate on tightly closed internal loops. Species shift from small generalists to large organisms engineered for longevity. Ultimately, total energy production perfectly equals total respiration. A climax community survives not by expanding rapidly like its pioneer ancestors, but by mastering absolute energetic efficiency and resource retention. This efficiency creates a logical trap. It is easy to assume that a massive climax ecosystem must offer broader, more forgiving ecological niches for the species living inside it. This graph reveals a counterintuitive reality. As ecosystems mature, individual niche widths drastically decrease. Early pioneers are generalists, occupying broad niches with minimal competition. Conversely, immense biodiversity in mature forests creates intense competition, forcing species to hyper-specialize into extremely narrow ecological niches. Ultimately, the climax state exists as a localized, relentless dynamic equilibrium. It is a massive biological system maintained entirely by constant, internal movement, rapid exchange, and continuous localized turnover. The math perfectly balances. Nutrient uptake from the soil is perfectly offset by release via decomposition, creating a resilient loop that repels external invasions. Ecological succession culminates in a specialized balancing of competition that maintains the system's permanence.